Okay. Probability distributions. You haven't seen these before, okay? But they do stem from probability tree diagrams. It's a way of putting all of your different possibilities all into a table with all the probabilities for each possibility in that table. So, and often with some of the examples that are going to follow on, we're going to need to draw tree diagrams to work out the probabilities for each event happening before we can fill in our table. But once the table's filled in, it's easy, okay? So, discrete probability distributions. So discrete data, different to continuous data. It's numerical data, data that can be counted, all right? So suppose that the sample space of an experiment can be listed, meaning that it can be written down in some order. And suppose also that the possible outcomes, usually called values, are numeric, right? So you learnt about this in stage 4, two types of data, numerical, categorical, or numerical or quantitative. And then we had numerical or quantitative, discrete or continuous. Discrete can be counted, continuous is measured, like length, height, weight, temperature, okay? Discrete can be counted, like how many pets, etc. All right, then, so these numerical values, so these possible outcomes together with their probabilities are called a discrete probability distribution, and it can be drawn up in a table. And we're going to do an example of one. Example, 4 coins are tossed and the number of heads is recorded. The following probability distribution table can be formed or created. See, if I toss 4 coins, couldn't I get no heads, 1 head, 2 heads, 3 heads, or I could have got 4 heads, okay? So there are 5 possible outcomes for the number of heads, and they are no heads, 1 head, 2, 3, or 4 heads, okay? So remember, my experiment is 4 coins are tossed, and the number of heads is recorded, okay? Now, the thing is, my outcomes are that I could have 0 heads, 1, 2, 3, or 4. But if I start drawing a tree diagram, right, first coin, second, third, I was going to do this on the board, but am I running out of space? And fourth, you can see that this is quite big, and I'm not going to fit it. This is bad. So it doesn't fit, right? It doesn't fit. But let's see if we can work out at least some of them. Now, what is the probability of no heads? Wouldn't that be tails, 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 no heads? Isn't that 1 out of, do you know how many things out of 16? There are 16. See, 1, 2, 3, 4, 5, 6, 7, 8, that's halfway, there's 16. So it's 1 out of 16. Let's do the probability of 4 heads, because that's nice and easy. Probability of 4 heads, same. That would be head, head, head. 1 out of 16. Now we just need to work out how many just have 1 head. Well, it can't be this or this branch. It could be head, tail, tail, tail. There's 1. Tail and all heads. There's 1. Oh, no, 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 it's not. I just want 1 head. Tail, head, tail, tail. There's 1. Tail, tail, head, tail. There's 1. Tail, 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 head. See if there's, sorry, students, it's 4. If there's 1 head, how many do you think there'll be with 3 heads? That means 1 tail. Wouldn't it be the same? And the ones, sorry, that's 4 on 16. And the ones with 2 heads, tell me a smart way to do this. Well, if I've got 1, 2, 4 there and 4 there, that's 8, 9, 10. How many would be 2 heads? There'd be 6 of them. And you could go in and count them if you wanted. How do you know that there would have only been 6? Because there are 16 elements in the sample space, and the sum of all the probabilities is what? 1. Yeah, it'd be 6. The sum of all the probabilities is 16 out of 16, which is 1. Okay? So, this, what I've just drawn here is a discrete probability distribution. It shows each of my outcomes and its probability. That is a discrete probability distribution. Okay? So, as we were saying before, this has all got to do with random experiments where okay, so just some new terminology. A deterministic experiment is an experiment with one possible outcome. This is not deterministic because I've got 5 possible outcomes. Right? An example of something deterministic is I'm going to choose I'm going to choose a girl from this class. What is the probability that it is a girl? Well, there's only one outcome, a girl. Okay, so a deterministic experiment has a probability of 1. There's only one outcome, and its probability is 1 or 100%. Okay, a random experiment is an experiment with more than one possible outcome, and that's what we're dealing with. We're not dealing with deterministic experiments. Okay, and a random variable. So we're just going to look at terminology now. So a random variable, usually denoted by an uppercase letter such as an X, is the result of running a random experiment. And a random variable, we know that variables can be numeric or categorical. Okay, but we're just dealing with numeric ones at the moment. Okay, now, in the above, like in the example above, what we did, our example, throwing 4 coins and recording the number of heads, is a random experiment because there is more than one possible outcome. You could get 1 head, 0 heads, 1, 2, 3, or 4 heads. Okay? If X equals the number of heads when the 4 coins are thrown, it's called the X, the number of heads thrown, is called a random variable. So from the table above, tell me what the probability that X is 0 is. What would I write? 1 on 16. What's the probability that X equals 1? Yeah, 4 on 16. Probability that X equals 2 is 6 on 16. So instead of writing here probability, I could write the probability that X equals X. So we're just looking at the terminology here. Probability that X is 3 is 4 on 16. And the probability that X is 4 is 1 on 16. Now, the way I really should be saying it is, what is the probability that X takes the value of 0? What is the probability that X takes the value of 1? Okay? And so on. What happens if I asked you, what is the probability that X takes the values less than 3? What would you do? You would add any of the ones less than 3. So you would add those 3, which is 1 plus 4 plus 6, all on 16, which is 11 on 16. So that's the probability that X takes on the values less than 3. And the probability that X is odd is the probability that X takes on the values of 1 or 3, which is 4 on 16 plus 4 on 16, which is 8 on 16. Now, instead of writing, so from now on, we are not going to write the following: number of heads probability. We're going to replace the word probability with what we've just done with, so we've got X is what our outcome could be, and the probability that our variable is little x. So this is under here, the probability that my variable is whatever little x is, it's 0. It's like a table of values. So we write it like this: the probability that x, my random variable, equals this little x. So this is just asking that the probability is 0 and just filling in the same values again, 1 on 16. The probability that x takes on the value of 1 was 4 on 16. The next one was 6, then 4, and then 1. So main thing here is that we know how to write out our probability distribution like this: little x and capital P bracket capital X equals little x. The probability that my random variable will be whatever little x is in the row above. Okay? Now, Notice that in a probability distribution, these must be non-negative. They're all positive. And the sum of all the probabilities has to add up to 1. If I add them all up, I get 16 on 16, which is 1. Okay, so the distribution, so yes, you can draw up a probability table, probability distribution table, but you could also graph it with your outcomes on the horizontal axis and your probabilities on the vertical axis. Notice in this case, it's symmetrical. Okay, so I've got when x is 0, its probability is 1 on 16. When x is 1, its probability is 4 on 16. You know, it's just like doing a set of points, x, y points, the x value and the y value on a grid. Okay, so it can be graphed as well. Again, looking at the types of data, we've got categorical data is when data is not numeric, rather words or objects or some sort of description. Okay. Numerical data, remember, is discrete or continuous. Discrete numerical data can be counted. Continuous numerical data is measured, as we said before. Now, we saw this before, okay? So a discrete or categorical probability distribution is called uniform. Be careful here. If all the probabilities, if the probabilities of all its values are the same. The example that we did was not a uniform probability distribution because all the probability values are different. Now, an example where, so here is an example of a uniform discrete probability distribution. It would be just throwing a die. So if I threw a die, what are my outcomes? 1, 2, 3, 4, 5, 6. See, that's just throwing one die. If I threw 2 die and I did the sums, it wouldn't be uniform. All right. So my outcomes are 1, 2, 3, 4, 5, 6, throwing a normal die. Okay. Draw the probability distribution table. Remember, this is uniform because all the possible outcomes have equal probabilities. What's the probability that my outcome is 1? And 2? Do you get why this is called a uniform discrete probability distribution? Because all the probabilities are the same. In the example we looked at before, they're not the same. It wasn't uniform. Okay? All right, now, remember I used the words deterministic experiment before? All right, an example, if I throw 4 coins into an empty bucket, how many coins are in the bucket, assuming I've got them all in? It doesn't say. So the thing was, I threw 4 coins into an empty bucket. They got in there. How many coins are in the bucket? Well, the probability that x is 4 is 1. It's not like I'm playing a game and I'm trying to see how many I get in the bucket. That's not what's been defined as my event. It says that it all is there. Okay, so because there's only one outcome, which is 4, the probability that we will get 4 coins in the bucket is 1 or 100%. Now, just looking at how we list the values of the sample space. So any finite set can be listed. So the whole numbers and the integers, so for example, you can see here 0, 1, 2, 3, 4, and that goes on and on and on. And the integers, which are positive and negative numbers as well as 0, can be listed, but they do not form finite sets. So some example of something that can't be listed are the real numbers in the interval from say 0 to 1. Remember, real numbers include rational numbers. They also include surds. So real numbers also are rational numbers and surds, and there's just an infinite, number of numbers that you would have to choose. Okay, so you can't list them. Now, just one more example here. Wolf has decided to keep tossing a coin until it shows heads. So Adolphe is counting how many times he tosses the coin. So the idea is you toss it and you might get tails, and then you toss it again and then you might get tails and then a heads. So what is the probability distribution for this experiment? Now, this experiment could keep going on and on and on. He could get a head on the first toss, or he could get a head on the second. or he could get ahead on the third toss or the fourth or the fifth or the nth toss. So the probability that he requires only one toss to get ahead would be the probability of ahead, which is just a half. Now the probability that he requires two tosses, if I start drawing up a tree diagram, I'll just draw one here, head, tail, that would be one toss. Then we've got two tosses, second toss, head, tail, head, tail. So if you require two tosses to get ahead, it means you would have got a tail first and then a head. So it's a probability of a tail times a head. We know that's a half times a half, which is 1/4 or a half squared. Now, the probability that he will require three tosses. So the diagram will continue, but you would have needed a tail, and then a head, okay? So if you require three tosses just to get one head, it would have been a tail, and then a head. Now we know that's a half times a half times a half, which is 1/2 cubed. And I could write it as an eighth if I wanted. If he required four tosses to get a head, I would continue here, tail, 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 then he would have got a head. So it's a half times a half times a half times a half, which is 1/2 to the power of 4, which is 1/16. Now we can see a pattern here. So if he requires one toss, it's a half. Two tosses, 1/2 squared. Three tosses, 1/2 cubed. Four tosses, 1/2 to the power of 4. Five tosses would be 1/2 to the power of 5, and n tosses would be 2 to the power of n, 1/2 to the power of n would be there. Okay, looking at question 8. So in a lot of the questions you are going to require a tree diagram. So a pack of 52 cards has 52 cards, of which 12 are court cards. In other words, a jack, a queen, or a king. Now, a card is drawn at random and is recorded whether or not it is a court card. So they're picking up a card and they're seeing whether it is a court card or not. The card is then put back in the deck, it's replaced, and a second card is drawn again. And then it's recorded as to whether it is a court card or not. So we have to draw up a tree diagram to see our possible outcomes. So our first card, well, it could be a court card or not a court card. And our second card could also be a court card or not a court card. Court card, not. So we need to put our probabilities on the branches. So we know that we've got 12 court cards, 12 out of 52. So there'll be 40 that are not court cards. And now, if the first card was a court card, it doesn't matter whether it was or not, because the card is replaced. So the second probability will be identical. 12 out of 52 for a court card, 40 out of 52. 12 out of 52 and 40 out of 52. Now, of course, this would not be the case if the card was not replaced. Okay, so the card is replaced, so the probabilities for the second card are identical, which is why we've got identical stages for this particular question. Now, it says, let X be the number of court cards drawn. Use the results from your probability tree to draw up a probability distribution table. Now, okay, we have to define what our what could happen. So we could either have, let's see, 2 court cards, 1 court card, not a court card, and a court card. So we could have 2 court cards, a court card, and not a court card, and a court card, and not 2 that are not court cards. Now, if X is the number of court cards drawn, so remember we've got probability that X equals X down here. So you could have 0 court cards, we could have 1 court card drawn, or 2 court cards drawn. So it's really important, you need to really think about how you're going to draw this table up. So if X is the number of court cards drawn, then your sample space for X would be 0 court cards, 1 court card, or 2 court cards. So that's what goes on my table. Now, the probability of no court cards is 40 out of 52 times 40 out of 52, which is 40 squared over 52 squared. The probability of one court card would be these two. So that's 0 court cards, okay? Probability of one court card would be 12 out of 52 times, so probability of one court card would be 12 out of 52 times 40 out of 52, and 40 out of 52 times 12 out of 52, so times 2. Now, we could actually work these out. I might actually work that out. I'll replace that with, may as well just work it out, which is 100 over 169, and the next one you can do that as well. And you would get 60 over 169. And the last one, always work them out. Probability of two court cards would probably be the probability of C and C, which would be 12 over 52 times 12 over 52. And you can work that one out. That's 9 over 169. So we've just got to make sure that, so we've done that, okay, our three probabilities, and just checking that the three probabilities add up to 1. So we've got 100 plus 60 plus 9 all over 169, which is 169 over 169, which is 1. So we know that that is correct. Okay, so that's question 8 from the exercise. All right, let's have a look at question 10. Now, this question also involves a probability tree diagram, but the stages will be different, each stage, because the sampling is without replacement. So before you decide to draw up this table, you need a tree diagram to determine the probabilities that go in the second row of the table. Okay, so we've got 5 tiles marked E, 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 R, and T. They are turned upside down, and 2 are selected at random, one after the other. It says draw up a probability tree diagram for the 7 possible selections of 2 tiles. So let's see what we've got. So the first tile could be an E, an R, or a T. So that's our first tile, tile 1. Now there are 3 E tiles, 1 R and 1 T, so we've got 3 out of 5 chances. Probability of an E is 3/5. Probability that you've got R is 1/5, and the probability that you get the letter T is 1/5. Now, if you chose the letter E first, you could still get another E or an R or a T. If you chose the letter R first, the only R is gone, you could only get an E and a T. And if you chose a T first, the next 2 letters that you could choose from would be an E and an R. So if you chose an E first, there's only 2 E's left out of 4. If you chose an E first, there's still the 1 R left out of 4 and still the 1 T left out of 4. If you chose an R, you've still got your original 3 E's left and your 1 T. And same here, if you chose a T, you've still got your 3 E's left and only 1 R. So now, all our probabilities. So we need to put these into the probability distribution table. So we've got EE, ER, ET. Then we've got RE, RT, TE, and TR. We have to draw up our table. Okay, now to draw up the probability distribution table, it's really important that you look at how X is defined. So it says, draw up a probability distribution table for the number X of E's selected. So we can see here you could have no E's. So the number of X's selected, so our sample space is number of X's selected, so you could have no E's, 1 E, or 2 E's. So we've got 0 E's, 1 E, or 2 E's. Okay, now, all right, so the probability that X equals little x. So 0e's are the ones that I have put marks on. So 0e's, so the probability of RT or TR, which is 0e's, RT is 1/5 times a quarter, and TR is 1/5 times a quarter. So that's 1/20 plus 1/20, 2/20, 1/10. Okay, or I could write it as 2/20. Actually, I might keep it as 2/20. Okay. All right, the probability of 1e. Now that would be this. So there's a few of those, 1, 2, 3, 4 of those. Or why don't we look at the probability of, we can look at 2e's as well. We might do the EE first, which is 3/5 times 2/4, 2/4, which is 6/20. So that's 6/20. And we're hoping that 6 plus 2 is 8, and we're hoping that this is 12/20. So 1e, it's going to be 3/5 times a quarter plus 3/5 times a quarter again. So those two. Then it's 1/5 times 3/4. And then it's 1/5 times 3/4 again. And just seeing what that totals to. All our denominators are 20. We've got 3 plus 3 plus 3 plus 3, that's 12. So 12/20. We can see, I'm just going to do a check column here for my sum. It's 20 out of 20 or 1. So I know that that is correct. Okay, so that's our probability distribution table. You don't really need this last row. And here you would just write really 0, 1, or 2. Okay, because that is the number of e's. Now just a few other questions. It says find the unknown constant A in the following probability distribution. Use the fact that all the probabilities are between 0 and 1 and that the sum of probabilities equals 1. So we know that the sum of all probabilities equals 1. So we can do that 4a plus 2a plus 9a plus 3a plus 7a is 1. That's the sum of our probabilities. So that's 25a equals 1, therefore a is 1 over 25. Okay. And question 11, it says a small pack or a pack of small cards consists of 3 4s, 2 5s, and 2 2s and 1 5. It says the suit is not imported for this experiment, and a card is selected at random and the value is recorded, and the card is then returned to the pack. So there is replacement here, and it's repeated, and you have to complete the probabilities for the outcomes of the categorical random variable x in the following table. So you're going to need probabilities of 2 2s, 2 4s, 2 5s, a 2 and a 4 in any order, a 5 and a 2 in any order, or a 4 and a 5. You have to draw up your probability tree, and 2 cards are selected. So you're wanting to be looking at what the first card is and the second card. So make sure you put those headings on your probability tree diagram. So you could either choose a 4, so we could have a 4, a 2, or a 5 as our first card, and our second card. So you might want to put your probabilities on those. You can do that from here. 3 4s, 2 2s, and 1 5. So 3 plus 2 plus 1. There are 6 cards altogether. So you've got a 3 in 6 chance. You've got a 2 in 6 chance and a 1 in 6 chance. Be very careful. There is, especially down here. So you'd only put 2 branches from here because there's no more 5. So if you pick up a 4, you could still pick up a 4, 2, or 5. If you pick up a 2, you could still pick up a 4, 2, or 5 as your second card. But if you picked up a 5 first, you've only got a 4 and a 2 remaining. Just spend a minute just filling in the probabilities on those branches and complete the table. So if 1 4 was chosen, there's only 2 left out of sorry, no, it's returned. So identical probabilities on both branches. Okay, so we've got 3/6 again, 2/6. Sorry, so this changes, made a mistake there. That is a 5 because the card is selected at random, it's recorded, and then the card is returned. So I do have to put that 5 back there. Again, we've got identical probabilities on all of the branches. Okay, now you can take a minute to fill in the probability table. So you might just want to start from the top if you want. So 2 4s would be 3/6 times 3/6, which is 9 out of 36. Sorry, 9 out of 36. 2 2s is here. That would be 2/6 times 2/6, which is 4 out of 36. You've got 2 5s down here. 1/6 times 1/6 is 1 out of 36. Now, when you do a 2 and a 4, you're going to need two things, a 4/2 and a 2 and a 4. So you're going to have to do both those. So 3/6 times 2/6 for that, or 2/6 times 3/6. Now, because there is replacement happening, the values will be the same. So you've got 6 out of 36 and 6 out of 36. That's 12 out of 36. And you can do the same for 2 5 or 5 2 and 4 5 and 4 5, 5 4. These are here of 2 5 5 2 and 4 5 5 4. So just putting those into the table, we've got 4 out of 36 and we've got 6 out of 36. Now, just seeing that these all total, we're just doing a quick check for the sum. So 4 plus 9 is 13. That's 14, 26, and another 10, that's 36. So the sum of all the probabilities is 1, and that's how you can tell that your table is correct. Okay, now a bag has 6 marbles, marked 1, 2, 3, 4, 5, and 6. 3 marbles are drawn in succession without being replaced. And the number of marbles with even numbers is recorded. So we're not going to do 1, 2, 3, 4, 5, 6. We're just going to put whether it is even or not even. Okay, so that's our first marble. And then we've got our second marble, whether it's even or not even. And then we've got our third marble, and looking at whether that's even or not even. Now, the probabilities on the branches is going to change because there is no replacement, and it also depends on what you've previously chosen. So, okay, now, so you're going to have to fill in this table first. You know you've got 3 even numbers and 3 that are not even, so 3 odds. So you've got 3 chances out of 6 of an even and 3 out of 6 for an odd. However, if you've just picked up an even number, then there would only be 2 left out of 5, but there would still be 3 left of the odds. Now, I could put not even or odd here. It doesn't matter. Okay, now if you picked up an odd number or not an even number, there's still 3 evens left and 2 odds left. So these are out of 5. I probably should put odd, actually. I might just change those. This might be easier. Now, if you've now on the third marble. Okay, so you've chosen an even. There would only be 1 even left out of 4, so there's still 3 odds here. If you've chosen an even and an odd, there are still 2 evens out of 4 and 2 odds. If you've chosen an odd and an even, you've still got 2 of each left. However, if you've already chosen 2 odds, you've still got 1 odd left and 3 evens. So now you can see your outcomes here. You could have 3 evens, 2 evens and an odd. Again, this is 2 evens and an odd, but in a different order. And here we've got 1 even, 2 odds. Okay, so you can write these out, but you don't put all of those in the table. You need to look at what X is defined as. And it says that X is the number of even numbered marbles chosen. So you can see here our outcomes consist of 0, we could have 1 even number marble chosen, 1 even numbered marble chosen, 2 or 3. So we've actually got 1, 2, 3, 4 different outcomes that could occur. 0 even, 1 even, 2 even, or 3 even. So 0 even is all odd. Okay, so just looking down here, 0 even is all odd, and it would be this last one, 3/6 times 2/5 times 1/4. Denominator is 120, numerator is 6. So we can work them out first, and then you've up here you've got 3 evens. So you've got 3/6 times 2/5 times 1/4. Looks like they are the same numbers. Now, if you want, you can simplify them. 6 out of 120 is 1/20th. So we can put those two in. So for 0 evens, it's 1 out of 20. And for 3 evens, it's 3 out of 20. Now you need to do 1 even, so it's these 3. And 1 even would be 3/6 times 3/5 times 2/4 for that one. It's 18 on 120. Let's just see if this one gives something. It probably will be the same. So this would be 3/6 times 3/5 times 2/4. I'd say the other one's the same. 3/6 times 2/5 times 3. Yep, 3/6 times 2/5 times 3/4. Look, all the numbers on the numerators is the same numbers on the denominator, just different order. So it's just going to be 18 over 120 3 times, which is 18 times 3, it's 54 on 120 for those 3. And you can simplify that by dividing by 6, it's 9/20ths. And the 2 evens should be the same as well. Whether it be 1 even or 2 even, because the odds are the same probabilities, you get the same answer again, 18 out of 120 for each. So adding 3 of those, 54 on 120, which is 9 over 20. Let's just check as well that the sum of the probabilities is 1, and it is. You've got 10, 10, 20 out of 20, which is 1. So that's your, in your table, that's your probability distribution table for X, which is the number of even numbered marbles chosen. So please just making sure that you're really being very careful about what X is defined as. Putting it there. That's the end of this video.